Hello. Kunal, am I still audible to you?
Yes, you are audible.
Yeah, so Kajino-san told me you were from BHU earlier.
Yes, I was. I did my master's from BHU,
So
specifically
what was
Institute of Environment and Sustainable Development.
so what was it on?
So I did my master's in atmospheric sciences. So it was my majors was in atmospheric sciences. It was a master's in science and environmental sciences, focusing on earth and atmospheric sciences. I worked with Dr.
Sorry, we
Kriparam,
can't
if you
hear
know.
you. Uh, Hello.
Hello.
Yeah, can you please repeat?
So am I audible now?
Yes.
Yeah, so I did my master's from Institute of Environment and Sustainable Development. So my master's was in environmental sciences, majoring in earth and atmospheric sciences.
So what was your
And
research?
so
Like,
I did my master's dissertation on crop residue burning in Punjab and Haryana, since my previous supervisor was associated with the Akash project. So I was also working on a specific facet of crop residue burning linked air pollution in Delhi NCR.
okay, so we'll start in, let's say, about 4 or 5 minutes. I'll, so how did you like you were starting in Tsukuba, right? So you already were working with Kajino-san before that?
No, actually, I was working in the same laboratory where I graduated, and then in BHU only. And then I was working there for like 1.5 year probably, and then I left that laboratory and joined uh, my new job at a startup in Delhi, and then I was working with carbon asset management, carbon finance, and so on and so forth.
Mhm.
And after that, I joined Kajiro Sensei in Scuba and
Okay.
started my work.
You was working with some carbon finance company before that.
Yes, I was into consulting, so I majorly do the assessment part of carbon budget, how much they should reduce their footprints and sustainability and their associated things.
Fine. So we'll just hold on for a few minutes and then we will join back in like 2, 3 minutes. Okay.
Sure, no problem.
Okay, good afternoon, everyone. So today we have a speaker from Tsukuba University, Japan, and he's a second year PhD student currently, but he has a rich experience even before starting his PhD into carbon finance, carbon assessment, and he did his master's as a mechanical engineering student. He was earlier from Banaras Hindu University too, doing his master's. And later he joined a private firm working into the carbon assessment thing before joining his PhD. So currently he's working in Tsukuba University. Kunal has rich experience in working with carbon assessment, and he is also working in collaboration with Mizu Kajino-san, who is working in Meteorological Research Institute. And today he'll be presenting his work on super resolution and using that downscaling, so creating super resolution surrogate for CMIP6 black carbon surface concentration using CNN data. So Kunal, it's all up to you now, and we welcome you here to this talk, and you can start your presentation. Thank you.
Okay, thank you so much, Doctor, for your kind welcome and your kind words. Let me just introduce myself to you. So my name is Kunal Mishra. I am from India, specifically from UP, and presently here doing my PhD work as a collaborating student in Meteorological Research Institute. I am focusing on carbonaceous aerosols, and right now my species of interest is black carbon aerosols. And thank you so much for having me, and I'll just begin the presentation now. So the topic of my presentation is super resolution surrogate downscaling of MRI-ESM2. That is the recent Earth system model of MRI, which is used for the CMIP6 project. And we are downscaling its black carbon surface concentration uh, to a downscaled resolution. This is a joint work done by me, Professor Kajino, Dr. Sakayama, and Dr. Oshima. So, yeah. So let me just introduce you a brief idea about why we are focusing on black carbon specifically. So black carbon is a short-lived critical climate forcer, which is significantly impacting air quality when it comes to the developing nations and also developed nations. It impacts meteorology and increase the health risk burden, particularly impacting the cardiovascular and pulmonary linked morbidity and mortality. We have a lot of global climate models for this black carbon surface concentration, which mainly targets about radiative forcing, how exactly the emission will target the radiative forcing, and so on and so forth. But there is a specific angle to the black carbon surface concentration, that is how it is impacting the future of the air quality. So my job was to assess how important is the black carbon when it comes to future scenarios, specifically targeting and specifically focusing on the air quality. So ESMs provide a coarser level of resolution when it comes to CMIP and the global concentration. And in order to assess the city level hotspots, city level cold spots, and their changing dynamics, we need to have a very fine resolution, at least to the municipal level or a city level resolution, in order to identify and isolate those hotspots and target them properly. On a global scale, black carbon impacts can be understood with different CMIP stages. So we have multiple CMIP stages and SSP scenarios, which targets how exactly the emission is changing, what are the dynamics associated with it, and so on and so forth. And once we have this particular coarse resolution data sets, in order to have any actionable points from them, we need a dominant and a specific super resolution. So there was a resolution gap since CMIP aerosols. So I'll use this CMIP6 and ESM2 interchangeably. But when I use CMIP6, I specifically mean a specific model, that is MRI-ESM2. So the CMIP6 aerosols has roughly around 200 kilometer resolution. So exactly, if I talk, then it is 1.8 degrees cross 1.8 degrees, and this is quite a bit coarse resolution, and it cannot resolve the urban-rural gradient. Also, it cannot identify and isolate which hotspots are contributing globally, and this in turn reduces our assessment on air quality and health burden assessments. So whether you want to do any adverse outcome mechanism, whether you want to do any health modeling, so you need finer resolution, finer hotspot identifications. So our job was to resolve it. So actually, we wanted to have it resolved to the city level concentration, city level resolution concentration. So we specifically focused on NASA MERA 2 product. So we resolved. So we had the input of 1.8 degree cross 1.8 degree, and after the spatial resolution enhancement, we obtained the MERA resolution, that is zero point 0.6 cross 0.5 degrees. So this is roughly around 50 kilometers cross 50 kilometers resolution, which is good enough to target, or good enough to, you can say, isolate and identify specific black carbon hotspot regions and hotspots. And this particular study has a very specific research objective to develop a deep learning framework, specifically using the convolution neural network based downscaling technique to downscale CMIP6 BC concentrations. Our first challenge and first step was the model development. We chose enhanced unit architecture with channel-based attention modules, which is the benchmark when it comes to the image-to-image classification and image-to-image resolution, since it is a established technique which is dominantly used by a lot of convolution neural networks. So we chose this particular technique. And then our second step was performing the evaluation. So we trained the model, we developed the model, we trained the model, and we did the evaluation. So evaluation we did on two major aspects. One was the global, the second was our regional scale. So exactly how these regional hotspots are contributing, and what is this our model good enough to identify the regional scale or the regional paradigm of the black carbon surface concentration. And the third and the last step was to apply this particular model into resolving the future SSP scenarios and get a hold of what the future air quality will look like as per the different SSPs. Now, for data inputs, we have the first input as a CMIP6, that is MRI-ESM2. So we targeted a specific variable known as surface concentration, and this variable name is given as per the model documentation SCONC-PC, and the grid resolution was 192 cross 96, and the resolution in degrees is 1.87 degrees cross 1.87 degrees. We specifically targeted the monthly mean, and the aerosol model was in specifically used in this particular global climate model was Magnisa. Our next target resolution model was BCS mass, and the grid resolution was 576 cross 361, and the resolution was 0.6 degrees cross zero point 0.5 degrees, and the temporal resolution was similar, the monthly mean. And the aerosol model specifically in MERA 2 is the go-card. We divided the training data set into, we divided the whole data set. So our biggest challenge in this study was not all the data is available with us. So the MERA BC carbon data is, BC surface concentration data is available from 1st of January 1980 up till now. So our major challenge was to downscale and have an effective downscaling model in this data scarce condition. So we divided this split into 31 years of training period. So 1980 up till 2010 was our training period, followed by a validation period of 6 years. So we opted for 2011 to 16, and then we have the independent data set of 2017 up till 2020. Uh, Now, the model architecture is enhanced unit with channel-based attention modules, with residual blocks, and a skip connection mechanism. So this is how the model looks like. So in the you have basically three cross sections here. So you have this part is particularly focusing on the encoder plot. This is the bottleneck. This is the deepest part of the model, and this is your decoder block. So your input gets upscaled here, then matched, and then through strategic refinement, we go to the bottleneck, and then we proceed to the decoder block where all the features are enhanced, and the final we get this output of the MERA2 resolution. We opted for skip resolution and skip connection mechanism specifically because of the reason. If let's say we have a non-homogeneous region, let's say we are target if the model filter is moving towards something on the East Asian, or let's say in the Indonesian part, where the homogeneity of the concentration, the grid pixels are not very homogeneously distributed. So this skip connection helps the model to identify and skip that part where we have ocean and the land, and those ocean land gradient and divergence is quite large, and the heterogeneity is quite severe. So this skip connection helps the model to skip those part and learn to next feature, which is much more important. And this particularly model has 62 million parameters roughly. And we have the encoder depth of 4 levels. The activation function was the leaky rectified learning unit. And the normalization which we used here was the batch normalization. This is the specific model network diagram and the workflow. So you can see we have two sets of training data input. One is the coarse and the one is the fine. So this is the reanalysis. We use the JRA nudge data. This goes into the model. So this particular model layer operates into three specific shift and three specific training scripts. So we have one model which is fixed. We have training script, which is moving towards the configuration and the model. So we have model configuration. This is where we used to do all the hyperparameterization in order to do the fine tuning of the model. And then once this particular process is completed and our model is finally trained, then we get a trained model, and then we do the testing part, and then we get the final output. So it is an enhanced unit with the channel-based attention modules and the residual blocks. So just the parameterization, what we used is the input dimensions. Since it is the input dimension was 192 cross 96 cross 1 because it was the monthly mean data. So each image is considered as one temporal month, and the output dimension was 576 cross 361 cross 1. That is same as the MERA output, which MERA gives as an output. We have roughly 62 million trainable parameters with the base filters of 64, encoder depth of 4, and the decoder depth is also 4. And we have one bottleneck which acts as the conjunction point between the encoder and the decoder block. We used specifically RSME optimizer with the beta values of zero 0.9, and both the beta values were 0.9 and 0.999. We also tried using Adam instead of RADAM, and we found that using RADAM was much more sophisticated, and it increased the training stability when it comes to the downscaling. We fixed the learning rate as 10 to the power minus 4, and we opted for a batch size of 8. Since we had a restriction on GPUs, we have only two A2 series GPUs when we were doing this particular exercise. So at two NVIDIA A2 16 gigs each GPU, we were using 100% of the GPUs, and the total memory allocation was roughly around 13 gigs. So each GPU used 13 gigs of each memory with 100% utilizations. The training time was around 1 hour or so, and we opted for a specific kind of a loss functions, which I'll discuss in the later slides. We also opted for an early stopping mechanism in order to prevent the model from overfitting and instabilization. So let's say if my model is giving same values of RSME, same values of gradient, same values of R square, then the model, if this pattern continues for a long period of time, and this long period of time is set as 15 epochs, then the model will exit out, or model has two options majorly. One is to reduce the learning rate or just exit out from the training code and give you the best model which is trained from all these parameters. Then the most important and the specific thing which when we discuss upon on anything which comes to machine learning based architecture is a loss function. So identifying and choosing a particularly good loss function when it comes to downscaling is a bigger challenge to us. So we opted for RSME, which is the benchmark when it comes to pixel-wise losses. So identifying pixel-wise losses. So we chose first RSME. This gives us a good idea about how the reconstruction accuracy is there in the reconstructed images, and we by using RSME we can reduce the pixel wise errors. The next was our SSMI. So SSMI is Structural Similarity Index Measure. So it basically gives us an idea about how features are matching from your input to output. So let's say if you are targeting a hand, how exactly the hand is reconstructed in your output images. So it gives us structural similarity, luminance, contrast, and structure. So we fixed the weightage of these two as zero point 0.4, zero point 0.4, and then one more thing we used is gradient as a loss function. This gradient help us to decide how exactly the edges are formed, because since we are talking about identifying the hotspots, so when we are talking about, let's say, city level hotspots, and let's say if I want to target Nainital or Dehradun, so I need to have a very good boundary on the grids when it comes to Dehradun or Nainital in order to assess which grid is contributing more and which grid is contributing less. So this gives us a spatial gradient preservation and hotspot boundary sharpness. So we can have a particularly sophisticated hotspots identification. And then the total loss comes as zero point 0.4 times of zero point 0.4 weightage of RSME plus 0.4 of 1 minus RSMI plus 0.2 of the gradient. Why we used combined loss functions? First is RSME alone cannot do the job. So let's say if you are identifying the pixel wise losses. So if your image is homogeneous, then it is not a big deal. You can identify and you can use RSME alone. And this will give you a good idea about how pixel wise losses are operating. But when it comes to a BC surface concentration values, and since BC is notoriously known for having a good spatial heterogeneity, so you cannot say that the North American BC concentration is same as the East Asian concentrations. You cannot say the East Asian concentration is same as the Siberian concentrations. Furthermore, you cannot say that in Indo-Gangetic plain, the distribution of BC is same as in the Southern Peninsula. So these all factors are responsible, and these all factors must be taken care of when we are trying to do some image to image downscaling. So that's why we didn't use RSME alone. Plus, why we used SSMI, as I already told you, it provides a good idea about the structural integrity of the reconstructed images, and when it combines with gradient, you can get a good structural similarity, you can get a good luminance contrast. And when you have a gradient in place, you can also identify the sharpness of the boundaries of each grid with much more accuracy. Now I come to discuss, now I'll be discussing the results. So we did the abolition study also when it comes to the neural network training, because our whole job was to focus on,
Hello, Kunal.
yes, please.
Yeah, so before we proceed on the result side, I was having some
Yes,
clarification query on the model setup and all those things.
yes,
So,
please.
as I understood, present model is 1.875 resolution model, right?
Yes,
And you will be basically doing the global simulation, not the over any specific region.
yes, it is a global downscaling model.
Yeah, okay, okay. No, so my first thing, like
Mhm.
there are, is there any other global model which is having already producing the data of 1 kilometer, 1 degree or half degree resolution apart from Mira?
So our job when we conducted this study, I'll answer your question by this particular point, that when we were doing this study, our job or our objective was to identify the most finer resolution available in the world. And
Okay.
when it comes to black carbon surface concentration, only Mera go-kart model outputs are having global outputs for BC concentration, which
Okay.
is overlaying with our targeted training temporal resolution. That's why we chose Mera.
So also like because Mira is already available. So what I
Yes.
see like basically here we are trying to explore the study or understand the procedural wise how
Mm,
your this new what new or whatever the new approach of
mhm.
downscaling is performing, right? That is the main our objective.
Yes.
Okay.
So our objective was of two folds. One was to have a architecture or a model which can give you a better, finer resolution
Mhm.
for global climate model. Since global climate model usually produces these sort of variables at a very coarse resolution. And when you're trying to do, let's say, if I wanted to have a specific kind of a model setup. Let's say I want to do WorfChem or I want to do something else. And if I wanted to have maybe super resolution data assimilation in any numerical model, so you need to have either you have an observational data or you have a reanalysis data or you have something else which can give you these sort of
Okay.
data
Yeah.
values.
Yeah. Fine. Fine. Yeah. Two
Yes.
more minor things. So
Yeah,
about
please,
your
please, please go ahead.
validation or the testing, that also you
Mhm.
are doing with the Mira or with some other source?
Yes, Mera only, Mera only.
Mira only.
So in
Okay.
in this
Yeah.
particular
Okay. Fine.
model
Fine. Fine.
configuration,
That's fine.
okay, yeah,
Now another last query,
please,
and you will
please.
be focusing only on surface, or you will also be doing at the different pressure level
No, right now we are doing only at the surface level
at the
concentration.
surface. Okay. Fine. Fine. Go ahead.
Yes, please. Thank you.
I'll just comment here one more thing that
Please.
he's trying to downscale CMIP6 data. So he'll be also using it to project it. So there may be ESM models that are doing current simulations, but his work can be used for the projections up to 25, up to years like 2050 or 2100.
Is showing projection or that is your another part of his study projection?
So yes, we have both the studies in place since this is the completed part of the work. The next part is ongoing. So we are doing
Okay.
the actual downscaling,
Okay.
and
Fine.
we'll be having that sort of paper very soon. So may I continue, please?
Yes, yes, please continue.
Okay, sure. Thank you so much for your questions. So, as I was discussing about the architecture, the framework, the configuration, and so on and so forth. Now, I'll show you some results what we got. And before showing you the results, I'll also tell you that we did some ablation studies also, and we specifically tweaked the architecture and we removed the channel-based attention modules and the residual blocks. So along with our obtained results, I'll show you how exactly the residual blocks and channel-based attention modules is specifically contributing when it comes to an effective downscaling models. So we have three models. So the SRCNN-BC, that is Super Resolution Convolution Neural Network Black Carbon, is the model which we're proposing. So this particular block contains UNet, CBAM, and residual blocks. So once we remove it, so this becomes this model, and after removing it, so this becomes only your SRCNN-BC plus residual blocks. And if you remove the residual blocks and your channel-based attention modules, you're only left with the unit-based CNN. And I'll show you how exactly these two things are contributing in the efficacy and effectiveness of the downscaling. So this is the results which we got. So as you can see on the first panel, you have total losses, RSME and SSMI. And this repeats into uh, the downward panels also. The first graph is your total losses. So this is for your unit channel-based attention module and residual blocks results. You can see very fine agreement between the validation and the training matrices, and the model is showing a good confidence, and a stability when it comes to the training performance. Following that, you can see in when you remove the channel-based attention modules, what you can see is there is a lot of instability when it comes to validation, and your model becomes more and more unstable, and this becomes more and more uh, vigorously visible when it comes to the removal of both residual blocks and channel-based attention modules. So even though you can ask me that why your SSMI is performing good, but your RSME and the total loss is performing not so good. So I can just tell you that when it comes to downscaling, SSMI is not an only matrix that you look upon. So this can give you the false result, the false positive kind of a thing, where your SSMI is quite good. And I'll show you the result that where SSMI is showing a very good results. However, you can see the pixel-wise losses is so severe, so heinous that you cannot use this model to do any sort of downscaling. So when it comes to the actual results, so our model got an SSMI of very good 0.002, which is very low for pixel-wise losses. We had a Pearson correlation R value of 0.8 and SSMI of 0.99. And this is not mentioned yet, but I'll let you know that the uh, noise to signal ratio is also showing quite good results when it comes to our training and validation performance. The SRCNN BC without CBAM is showing a very not very good of a very good of SSMI, but when you compare it with your root mean square error values and your Pearson-r values, you can see that how this picture is changing. And this picture is more or less similar kind of a thing when it comes when you remove the channel based attention modules and residual blocks. So you can see these two results can be understand on a similar lines. However, the model instability is more and more visible when it comes to the removal of both channel based attention modules and the residual blocks. Now, what about the testing performance? So we did an independent testing, and before I'll discuss you about the independent testing.
Kunal, can I have a question here?
Yes, please.
Yeah, did you consider the gradient here while calculating the total loss?
Yes, we considered the gradient. I'm not showing you the complete results. I'm showing you the results which we got because it is still in the process of manuscript submission. So once we have submitted the manuscripts, I'll show you the complete results. I can definitely communicate to you the complete results.
Okay.
So we use the combined loss functions on that. So on the testing performance, first and foremost, I'll tell you about the ablation studies, how ablation studies are performing. So we have found that the residual blocks has improved the training stability, the convergence speed, the CBAM specifically, the channel-based attention modules, which contains the both of the modules, your spatial attention as the channel attentions. So it basically focuses on what to focus and where to focus. So it tells the model where to focus and what to focus. And it improves considerably a lot when it comes to the Pearson-r values, which is image to image correlation and your R square values. And this combined effects gives us good values in the training and the testing performances, which is identified when we are seeing the downscaled images. And when it comes to matrices, we got an R square of 0.88 in the testing part. So this particular data sets, the 2017 up till 2020, was not seen by model anywhere. It was completely independent, and we did the testing on this particular uh, set of data. So R square was 0.8. Pearson values showed a very good result of 0.94. We have the Spearman correlations also. Again, the SSMI was similar kind of values, 0.99. RSME was very low, mean biased error, bias, and so on and so forth. So the IOU is showing 69.69.695, which shows we have an overlap of 69% of the hotspots. So I can tell you that we have gotten the high reconstruction performance on an independent test data. Now the global outputs. So as you can see is the first panel is your annual surface concentration. So you can see this A part is your global surface concentration for 2017 to 2020. This one is your input image. So this is MRI-ESM2 values. This is the downscaled, and this is the ground truth, that is Mira. So we treated Mira as a ground truth. Similarly, in the B part, you can see that this is for the spring season, and this is the input, this is the output, this is the ground truth. You can see that Mera sometimes give you an high concentration values, and sometimes CMIP shows the higher concentration values. This particular phenomena I'll discuss when I discuss the zonal and the meridional variations globally, and which is coming in the next slides. So again, so we have the spring BC concentration value. So this is an annual spring average of this period, and the C part is your summer, and the D part is your autumn. So you can see more or less, you can see the structures are same. These particular hotspots are very nicely identified. And when it comes to your spring summer season values, you can also see that this is particularly very nicely identified in the downscaling images. Now the regional analysis. So in the regional analysis, we found that the RSME by region, so in the Southeast Asia, so in the East Asia and South Asia, we found a lot of RSME. So RSME was particularly high in this region. The reason which we found was there is a lot of spatial heterogeneity when it comes to the East Asian regions, particularly the East Asian regions, and specifically the Eastern China regions. So this show, but due to this region, the model was showing quite a lot of RSME in this particular regions, and a similar kind of a pattern was seen in the mean absolute error kind of a graphs. And we can see the correlation is more or less similar, showing a similar kind of a trend, except for Antarctica. This was particularly the case because Antarctica has a very low concentration, and the model was showing some hallucination when it comes to these sort of polar regions.
Arctic is much better.
Yes, Arctic is much better than Antarctica, because there is a lot of land available in the northern hemisphere than in comparison with the southern hemisphere.
Okay.
Yes.
But low value is still, I don't think the value might be having that much difference between Arctic and Antarctic.
Yes, absolutely true. Absolutely true. But when you look at the relative scale of Antarctic and Arctic, particularly your Pearson correlation also is impacted by the local emissions when it comes to the Greenlandic forest fire emissions, the Canadian emissions, which are contributing into those regions. But when it comes to Antarctica specifically, there are no forest fire burning around those regions, except for, you can say, the mid-Australian forest fire.
Yeah. Okay.
Thank you. And again, one very important result that we got was when we talk about the bias. So bias was defined in our model was how much we are predicting subtracting it from the target. So how exactly our biases looks like. So in East Asia, we are also predicting more than we should have. So from target, we overshooted, and specifically in Asia, Antarctica, and Arctic, these particular things was observed. Reason being, in East Asia, a lot of spatial heterogeneity, and some grids was contributing very much, and some grids are contributing very low, and these grids are not very far located. That was the reason where by this model, when it formulated the neural networks, it shows hallucination as well as the increased number of bias. And in
Kunal,
Antarctica also, yes, please.
I also was wondering about the overshoot in East Asia. Could it be
Mhm.
because of the excessive grade, I mean, land sea gradient that we observe in many of East Asian nations?
So yes, this can be true, but we found something different when it comes to East Asia, particularly, and particularly if I'm talking about a specific region-based scenario, then particularly in the Eastern China part, where a lot of industries and the major Chinese industrial locations are situated. What was happening is in ESM2 there is a lot of overestimation which is already been reported. So
No,
one
but
factor
just
was,
hold on. But I'm
yes,
seeing
please.
like value-wise, if you see bias, the East
Mhm.
Asia value is not that much high. It is only sign different, positive and negative. If you see South
Yes,
Asia or Europe, they are having much higher value.
yes,
Their value is not high.
yes. So you have to look at this graph from a relative bias point of view first.
So
Second is,
value-wise, Kunal, as sir mentioned, so value-wise, South Asia is being heavily underestimated. Europe both, and it's only in East Asia that there is an overshoot.
let me just clarify it on a different sort of, by giving a different sort of examples. So as you have already been seeing that we are getting a very low pixel wise error. So our RSME was very, very low. So when you have an RSME in place, and when you look at the bias scores, this bias score will make much more sense. And when you look at the particularly the cases where we got a positive bias, so you have to look why positive and why some regions are showing very negative biases. So positive bias is coming from the inherited overestimation of black carbon surface concentration in ESM2, which is already been published and already been known that yes, a lot of ESM models are projecting overestimations in the East Asian part. So this is due to that particular regions. Also, the sea land gradient is a lot. The spatial heterogeneity contributed. Plus, this model was trained only using MERA and CMIP. So if we have included some population-based data, if we have included some metrology, then the model results will be something different, because the model doesn't know where exactly the population is located. So one very shocking result we got is in the middle of Siberia, we found one pixel showing a lot of black carbon concentration. That was specifically identified as a model hallucination kind of a case. So you cannot say that in the middle of ocean, a pixel is contributing to black carbon. But we do find one pixel contributing at the Siberian highlands, where no black carbon can be there of such an amount. So these all are the cases of model hallucination, and these usually happens when you do model training, when you do any neural network, the model hallucinates. Similarly, like when you ask ChatGPT a lot of things, sometimes it gives you an bad result, even though ChatGPT is trained on a billion parameters of data. So you cannot say one model is very good and one model is very bad. The hallucination can happen. So that is why these sort of values we got. Now I'll show you what I was talking about. So this is a very interesting graph which we got. So we did a intercomparison between the zonal and the meridional means. We wanted to see exactly how we are closer to the ground reality and exactly what is happening with our downscale modules. So you can see the green dotted line is your CMIP input. Your red dashed line is your downscaled version, and your blue solid line is your MERA. These lines which are drawn here, so the purple line are the developed regions and the red lines are the developing regions. Since we are getting a lot of researches on the black carbon that we are underestimating black carbon in the global south than in comparison with global north. A very recent paper was published in Nature where the authors have said that even when we do a lot of observational studies, a lot of um, uh, studies which exactly measures the black carbon surface concentration, it comes that the global north is underestimated. And when I tell you the results here, so you can see in the tropics and the regions where you have a lot of overestimation is dominantly visible in this graph. So zonal annual is showing good, and you can see we are very close to the MERA than with CMIP. So this shows that our model is trained on a good data, and the model is showing a close coherence and a mutual agreement with MERA than with CMIP. And this is what we wanted. So we wanted the model to come closer and closer to MERA, not closer to the CMIP. And you can see these regions specifically. So these Toronto, Seattle, these particular regions are there. And this is showing where MERA is showing more than CMIP, because up till 2014, the biomass burning emission inventory was of the observation and the real time. But post 2014, from 2015 onwards, the data assimilation of the biomass burning was fixed at a stagnant gradient, and a stagnant kind of a biomass burning emission inventory was assimilated in the ESM2. This was the main reason that you cannot predict forest fire before it happens. So in 2017, a lot of cases was reported in the Canadian Highlands, specifically targeting the southern western part of Canada, where we had a major forest fire events. So these are the summer forest fire events, and you can see this particular trend very sharply when I show you the summer zonal and meridional zonal mean results. So now when it comes to the meridional mean, again, I can tell you that we are getting a good value of good agreement value, except for the Seattle. So just above Seattle, the forest fire was there. And these were the regions notoriously known for the forest fires, the Canadian southern western regions, which are known for the forest fires. Also, a lot of cases have been reported in the Greenland also, where the Arctic forest fire is contributing a lot into the black carbon surface concentration. And this was majorly the reason behind why we got you know such an overshoot in MERA, but not in CMIP. But when it comes, when you correlate this particular trend with the East Asian nation regions, the CMIP has already been overestimating the black carbon surface concentration in the East Asia. And when we downscaled it with MERA, the closeness was coming to the MERA, and we got some sort of normalized results. But since there is not a lot of spatial heterogeneities and not a lot of emissions per se when it comes to the specifically the Canadian regions, the Greenland regions, and the Arctic. So this was more visible there in comparison with the East Asia. Now, in the DJF, that is in the winter part, you can see that again the CMIP is showing a lot of biomass burning. This is mainly due to the biomass burning, and the data assimilated here was already being overestimating. But our model is coming more and more closer to the MERA than with the CMIP6, and this was the same trend which was observed here also. Now, when it comes to the spring part, so in spring also, you can see it is underestimating it in the regions of Seattle, Tokyo, and so on and so forth. However, in the spring also, there is spring biomass burning, and this particular divergence is due to the biomass burning. Now, in the summer part, so this particular trend, which I was discussing you about, was now much more clearly visible here, where you got in the Arctic, the biomass burning is contributing so much, and the MERA is showing that yes, the biomass burning needs to be accounted and normalized when you are doing the actual downscaling. And of course, when you are doing the SSP scenarios downscaling, you cannot predict biomass burning beforehand. So you need to have an idea about the trend on the biomass burning, and this must be learned by the model that yes, biomass burning is more and more happening in the Arctic regions, and it is more visible in the MERA. And these particular graphs will give you why exactly our claim is justified. And then when it comes to final, the
Yeah,
September,
hello,
October, November. Yes, please.
Kunal. Can you go
Yes,
back?
please.
So, like
Which
the
season?
architect thing. So, did you try
Yes.
to check with your original model output before
Uh,
downscaling how it is behaving?
so you can see, so this dotted
Which
line
is
and
that
this blue line is the real model outputs. Only this
uh,
is the downscaling.
green dot
We
line?
have
Green dot
plotted,
line.
so the green dot line is the real model output, the ESM output. So we have plotted everything
I see.
together.
Okay, okay.
Yes.
So then why like Mira is, that means your real model output is also not able to capture, if you believe that it is biomass burning, so Mira
Yes.
is capturing that part,
Mm-hmm.
but
Mm-hmm.
your model is not capturing,
Uh,
like your original input model.
yes, of course, it cannot
Yeah.
capture
No, no,
because
no. Why I am asking this question? Because
yes,
I am
please.
slightly doubtful when you say Arctic biomass, means like where, which biomass you are talking, Russia, or where, which influence in Arctic, which biomass will be influencing?
So, in order to quantify and identify this, we
No, no,
plotted
no,
the.
no, no, broadly. I am not telling you pinpoint, but broadly
Mhm.
in Arctic, which region biomass burning will be having so much influence that level is touching to almost level of around 35 degree or 40 degree
So,
north.
two major regions, to be very specific, two major regions. One is the Western Canadian region, and the next one is the your Greenland region. So these two regions, the biomass burning was showing a lot of uh,
But
black carbon surface
any, whether
concentration.
have you seen physically the biomass burning fire count data or something? Because
So we
as per my knowledge, I have not seen such a fire count in those regions.
yes,
Where
you
this
cannot
level is
see
very
because
high.
this, yes, you cannot see it because when you try to focus your result on specifically on the year 2017 and the summer of 2017, you can see
I see.
a lot, a specific case was happening in the summer of 2017 where a huge forest fire was
But
happening in the
but
Canadian
this is
region.
average of 2017 to 2020, right?
Yes, and this particular and those events have contributed a lot significantly. Plus, there is also a lot of overshooting in the biomass burning in those specific regions. So in the Canadian regions, the events are not very long lived. They are short lived but high emission scenarios.
Yeah, but because they are extending from almost, you say, 55 degree to almost 70 degree or 6 something. So looking
Yes,
very, any, okay, go ahead.
and just to clarify one more time, so you can see this particular peak. Why this particular peak is happening here? This particular peak was the 2017 forest fire. This was majorly driven by 2017 forest fire in the Canadian
No, no,
region.
Seattle area, that is of course known in that, means in
Yes,
that around in that region. And
yes,
also peak is not that much high. Yeah, peak
yes,
is really very big and broad.
yes. And when you have a zonal mean, then when you relate it with the zonal mean, of course your concentration will overshoot.
Yeah. Okay, okay, go ahead.
Thank you, thank you. So I have shown you that again in the September, October, November, the autumn part is also showing a good coherence with MERA2. Our downscale version is showing a good coherence and agreement with MERA2, then with CMIP. And thus we can say that we are reducing the systematic bias of the particular product of the MERA, the MRI-ESM2. Now, this was all of the results which I have shown you. This is all that we got till now, and the study is continuing. We are also identifying exactly what hallucination cases are there, what exact hallucinations are there, and how to counter it. So, and depending upon the results, we'll definitely communicate to you the final paper when we have it. And when it comes to the discussion, now I'll discuss what we had. So the super resolution convolution neural network based black carbon downscaling model shows a close fidelity with MERA, then with MRI-ESM2, and this is very good uh, to identify the spatial heterogeneity and also the spatial heterogeneity, the biasness, and so on and so forth. The enhanced unit based CNN architecture with channel based attention modules and residual blocks have proven to be an optimal choice when it comes to data down when it comes to scalar data downscaling, specific in the case where you have a data scarce scenario. So if you don't have big data to train on, then you can opt for an optimized architecture that can give you a good results. And the visualization of the learned attention weights of your downscaling models demonstrate that the model assigns higher attention to the emission spots. This was due to the fact that we used the channel-based attention modules. So these modules help the model to focus where to focus and what to focus. giving us the learned rates are very much optimized. And the emission hotspots and the transition zones are where the concentration remains consistent with the physical expectations. A high SSMI and a R square indicate that spatial structure preserved and showing a remarkable fidelity. However, the strong performance obtained show the attention-based architecture can be used for downscaling, but the limited data is the result whereby we got the hallucinations. So we obtained hallucination in the few pixels, and this was the fact because we trained this model on a very small set of data. And also the pixel-wise losses such as mean absolute error or mean square errors produced by ensemble-like predictions can underestimate the extreme concentration and smooth out the final plume structures. So we are now moving towards using the generative adversarial neural networks and the diffusion models, particularly S3-based diffusion models. This is already going on, and the training is still going on. And to produce more sharper pixels, more effective images for downscaling. But yes, these all comes at a cost of huge computation. So just to give you an estimate on computational cost, so this model was trained on two A2 series GPUs of 16 gigs each. This particular model, the generative adversarial neural network, we are training on one A2 series 80 gig of GPU, and we cannot increase the size from one. So you can see how much memory is taking by one GPU. So on the conclusion part, yes, the attention-based unit with interpolation, pre-processing, and the refinement network acts as a good model, proves to be a good model, an optimized structure when it comes to BC surface concentration. And if you don't use channel-based attention modules, then you will not get much good results. The enhanced unit plus your CBAM modules gives you a very good RSMI, very good R square, the R values of Pearson-r values, the SSMI, and a good feature reconstruction, hotspots reconstruction, and with 1.6 times of spatial enhancement. So it works at regions where homogeneous emissions is there. So let's say if you are downscaling Africa, where the emission scenario is quite homogeneous, the locations where emissions are based off is more or less homogeneous, then this model works very, very good. But when it comes to the regions where the degree of variation in the spatial distribution of black carbon surface concentration is very, very high, then your model definitely faces the curse of hallucination. And this model was trained, again, I tell you, this model was not trained overlaying any population data. So model doesn't know where the population is there and where we have a very population less scenario. So let's say if I have used the population based data overlaying on the top of it, maybe using auxiliary data like metrology and so on and so forth, then it must not give me the pixel error where in the middle of Siberia where there is no population located. So yeah, so since it is not having much more auxiliary data, so supervised reinforcement learning was not possible. But however, we are trying to assimilate more and more auxiliary data, and we are trying to do much more sophisticated reinforcement supervised learning in order to get much more finer pixel resolutions, much more final results, and on similar lines. So it downscaled and it shows a closeness with MERA2 than with ESM, which is very good because you are reducing the general bias and you are getting closer and closer to the ground truth in comparison with your global climate models. And this was prominently important because when you're trying to do health assessments, when you're trying to do health modeling or financial modeling or any sort of these things, you need to be very close to the ground reality. You need to mimic the ground reality more sophisticatedly. And yes, SRCNNBC is demonstrating to be computationally efficient. So yes, it is a computationally efficient architecture. And yes, we are trying to extend the study to do some high resolution data assimilation for health assessments, for health modeling, and financial modeling. Now, the future work is our ongoing process. So we are doing, we have added the auxiliary data. We have refined the model, the architecture, and we are doing the training, we are validating, and now we are doing the actual downscaling of the future scenarios. In the near term, we wanted to do a multi-ensemble downscaling. So we wanted to have much more models in place. So all sophisticated models of CMIP6 for downscaling, so that our on an average, the ensemble downscaled product can give you more good picture of black carbon surface concentration. And in the midterm, we wanted to have multi-species downscaling also. So we wanted to extend this work to different scalar quantities like dust aerosols, like different other aerosols, some gas products also in the near future. And in long term, we wanted to have, we are in the process of developing a hybrid downscaling model, which can give you a super fine resolution at the end. So this is all the work which we are doing. And thank you so much for your patient listening. I'm very grateful to you for your time. And please, if you have any questions, please, I'll be happy to answer them. Please go ahead.
So thank you very much, Kunal, for also finishing well in time despite of all the questions. And I have a bunch of questions, but I'll first let the audience in the auditorium. So Vikas.
Thank you, Kunal, for the nice talk. I have a question
Thank you.
regarding the training data set. Like you have taken data from 1990 to 2010, and I have found that in the MERA data, like there is a sudden jump in the level of all the pollutants, including black carbon. So how did you manage for that in your training data set actually?
Yes, of course. So this was a question asked to me in the previous seminar also, that if you look at the emission scenarios, so emission scenarios changed abruptly post 2000. So let's say if I take a case of Japan, so Japan was very polluted in the 90s and the early 80s. But when it comes to the cases of now, it is not very much polluted, or I can say it is not a lot at all polluted with black carbon. So how did I manage it? So basically, you have to look at the architecture first. So the model is doing the image to image downscaling. So you have your high emission scenarios corresponding to those high emission scenarios. You have the MERA high scenario images. So this is not like I'm validating with something else. So because you have your training data sets and the model are trained on, so let's say if I take a case of specifically June 1985. So June 1985 CMIP data and June 1985 MERA data are trained together. So it is trained on the June 1985 data. That's why we are able to counter that particular problem. So the image to image downscaling is being optimally trained.
Hello, Kunal.
Yes,
That's a nice
please.
talk. I have a couple of
Thank you.
questions. So, in the result sections, you showed there was some underestimation and overestimations with MERA
Yes,
2. And
yes.
if I'm correct, you reasoned it that since the biomass burning data was, I mean,
Mhm.
in the
Yes.
emissions were not available. So, I mean, is it just the biomass burning which is, making it happen, overestimation or underestimation, or for metro regions, are you also trying to see is there any change in emission policies and how they are affecting? I mean, there could be multiple reasons why there are these underestimation and overestimations.
Yes. So let's take one by one of the model. So first and foremost about the ESM. So ESM2, how ESM2 and what factors ESM2 considers when it comes to predicting the black carbon. So usually most of the data, most of the methodology was assimilated with observation in the reanalysis and so on and so forth. But the biomass burning was one key element which was fixed post 2015. And this was the main reason why we attributed this escalation, this peak to the overestimation and underestimation. The second part is in the nudged outputs that we had from 1950s up till 2020, the JRA nudged data sets of the ensemble run, the particular ensemble run. So we dissected it much more in a much more finer details. And after reading multiple times the model documentation, we found that not much has changed, but yeah, your biomass was the key factor which was contributing in the black carbon. That's why we attributed the overestimation and underestimation of ESM to the black biomass burning. Now comes the MERA. So MERA usually uses the go-kart model, and this go-kart model uses some sort of reanalysis data and then modeling it and then producing the black carbon surface concentration. And since it uses the real-time biomass burning emissions, it uses the real-time impact of the black carbon reduction or increased policies, which can lead to both the increase or decrease policies and decrease concentration policies. So it attributes all the things. And that's why we took the baseline as MERA, and relating to MERA, we used the downscaling. So when you look at the MERA as the baseline and then you do the downscaling, your idea or your job must be to be much more closer towards MERA than with CMIP. And this is what we have obtained.
Okay. And one more thing, since you have mentioned in the future work that you will be including many other species in
Yes.
this model. So just very broadly, you can answer like what could be the things which would be changing, or the whole setup will be the same. I mean, if I'm talking about PM 2.5 or others, so
Mhm.
I mean, what will be the major change? And if not, if there are only minor change, what they will be?
So basically, I wanted to look at the major aspects of PM 2.5 and PM 10. And right now, my concentration is more or less focused on the carbonaceous aerosols. And I wanted to include dust aerosols and a few other species into it. So I'll be looking from the perspective of aerosols. And yes, PM 2.5, PM 10, coarse mode, fine mode fractions, this all are in the future work, future domain. But we have a very big limitation. So limitations comes from the computational cost. So you need to have optimized kind of architecture in order to do so. Plus, this work is going on the lines of downscaling carbonaceous aerosols. So yeah, maybe in future we'll include a lot of species, but not as of now. Maybe in the near future. So we are trying to do multiple species downscaling in the near future, not very near future.
Okay, any other questions? Okay, no one. I have two specific questions. So,
Yes, doctor, please.
Kunal, if you go to your loss slide where you have put in certain numbers to
Mhm.
SSIP gradient and
Mhm.
RMSE. So how did you reach to those numbers? Like by those
So
specific
how
numbers to calculate your
how
generalized loss? No, not here.
uh,
Before that,
can you please
no hypertuning the model.
hyper
The loss
parameterizing the
function.
model?
Yes, 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 yes. Here. The loss function you
Okay,
got. Yeah, you
okay,
had
this
particular point
yeah,
4, point 2, and point 4 again. So
okay. So since one of my co-author, Dr. Sakyama, is very prominently known for AI-based downscaling, and his very recent work was doing the mesoscale wind profile downscaling. And since he's one of the co-authors, so uh, we discussed to and fro on it. We formulated different permutation and combinations on the loss functions, and this particular loss functions works best for us. That's why we chose this one.
because these days there are a number of ways of hypertuning and which are uh, more grained into the kind of observed data you have. So maybe in future
Yes,
you can look at those options. So for starters,
yes,
this is yeah.
Yes, absolutely, absolutely, doctor. It is well known fact that in order to improve your performance, you need to have more and more sophisticated loss functions. And I'm very grateful to work with Dr. Sakayama, who is being doing the work on tailoring the loss functions depending upon the output. So he's very well known for tailoring out the loss functions and making a tailor fit loss functions to fit for different architectures and different
Yeah,
objectives.
because
So
ultimately, how close you go to your testing, I mean, the major in the ground truthing will depend on how good your loss function is. So,
yes, absolutely, absolutely true, absolutely true.
okay, the last question is like more of I want to know if this is your direction of work in future or not. Uh,
Yes,
see, uh, as you already mentioned, that having a good auxiliary data set would be much more improving your current results, right? Whether, I mean,
yes,
especially in terms of downscaling, like
yes,
incorporating the population density or the methodological data set. But in
yes,
your future work, you showed like using GN and going towards a bit more high computational side of models.
yes.
So, uh, and another thing is for which I didn't see in also your future works is that currently you are using Mira 2, which is fine, but Mira 2 is not probably at present the best to go for ground truthing because there are multiple multi-satellite uh, governed AOD data set which can possibly provide you even higher resolution data sets that you can use for long-term training of your CMIP6 model. I wonder if you
Just
are even
just
thinking
to
about this direction.
Okay, okay, okay. So the first question, the first comment or the question that you had was on the lines of whether we wanted to use any auxiliary data in the training. So yes, we are planning and we have executed the training on auxiliary data by using different methodology, using population, using multiple products, so that we can bound the training paradigm and we can have an effective training in place. So yes, we are on the similar lines and on the similar architecture too. And the next part that you had asked me or just commented or suggested me that using Mera is not a very good option to have, maybe in the current times. So I slightly disagree with you on that point. Reason being, let's say if you are saying suggesting, let's say if I use the blue algorithm of NASA in order to have a fine mode course or coarse mode fractions of the AOD or identifying the size segregation of aerosols. But if you wanted to derive black carbon from AOD or multi-satellite ensembles or some hybrid models, your uncertainty will increase into multiple folds. And even though you have very fine resolution black carbon, but I don't know what sort of uncertainty it will include and insert into the model. And since the CNNs or any neural network or any deep learning based models are known to be notoriously have these sort of uncertainties pre-trained. So they already had uncertainties, and if you don't use the product which has less and less uncertainty, then you are going to be a lot of your outputs will be a lot of uncertain and biased. So in order to
See,
have, yes,
uh,
so
yeah. So
our
basically,
whole
when
job
we
was to
say,
reduce the, yes, 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 please, please.
so basically when you have already mentioned that hybrid modeling along with satellite data,
Yes,
so that can already fix that problem. So you can have multi-satellite data set ingrained with your Mira 2 so that the cases such as the biomass burning one or urban like South Asian underestimation, those things would be significantly. Of course, you can
yes,
have.
absolutely, absolutely true. So we were initially we were trying to use the data sets available with AeroNet, Spartan, or on the similar kind of a things overlapped with AODs. But again, when your objective is very narrowed at a surface level concentration, and you wanted to have a 3D data, let's say columnar data, then it becomes a bit challenge. And yes, we are working on developing such models, but we are trying to have much more sophisticated ground-based observations to revalidate and reassess, rather than using ensemble modeling or
Yeah,
any
of course, if you
reanalysis
can
for
have
that.
ground-based, it's the best. Okay,
Yes, yes,
so
yes.
I'll stop for now. And we have with us Kajino-san also online. So, and Kawada-san from JMA is also with us. If I know Kajino-san is already a co-author in the work, but
Yes.
if Kawada-san or Kajino-san, any one of you want to say something, we would be happy to hear. Okay, so if not, we can close this session. Thank you very much, Kunal, for all your time and
Thank you so
bringing
much.
us your good work to us. And
Thank
we
you
wish
so
you all
much.
the best for your future endeavors. Thank you very much to you and the
Thank you.
audience. And we end the
Thank you. Thank
session.
you so much.
Thank you.
It's
Okay.
been an absolute pleasure. Thank you. Thank
Thank
you
you.
so much.